Hi, Sune.
Thanks, Kunal.
No, he'll arrive at 2 o'clock. There's a point where people David.
Okay. Must be earlier.
And I told him yesterday it was 2 p.m.
Can someone on Zoom please confirm that you can hear me? Excellent.
Oh, he's not there yet. try that.
So I heard that there's two people can follow online. Is that so? Other people online following?
Yeah.
Okay. Is the people that you've invited, are they typically francophone or would they prefer English?
They prefer English.
Okay, very good. Very good.
Marko, you're on this link here just to be sure. David is on another link. That's the one. No, but I'm just wondering what link I can follow. Okay. It's funny that one of the rapporteurs is one of the jury members is on the wrong Zoom link here. That's the link that you typed into the. You sent the wrong. Sorry, David. There's a problem with the Zoom link. Everyone's on the wrong link. Sorry. Just stay where you are. We'll send you the right link. What Zoom link did you leave? Did you send it? What Zoom are you on? What's the Zoom link you're on?
The one that you sent
No, it's not that one. It's not that Zoom link. Okay. That's the one? Because I made another link. Zoom Marko, is it the one? Sorry. Yeah, sorry about that, David. Can you hear us okay now? Okay, so I don't know if Ben, do you want to ask anything if David is online now?
Hi, David. Hello. I just have to have you. I've been designated president of the jury. Is that okay with you? Yes. Okay. Great. Perfect. Thank you. thèse. Maybe we can just quickly go through it, or we can say the name and the form so that you know who you are. My name is Dan Lambert. I'm a professor at Sorbonne University and here at the IOP.
Oh yeah, so I'm Henry Jordan McCracken. I'm one of Marko's. I'm Marko's thesis director with
research at Thesis.
And David Weinberg, Professor at Ohio State, London, New Jersey.
Thank you, David. We will have a presentation by Marko on his thesis work, which will be followed by a question and answer session. After the question and answer session, we're going to excuse ourselves and deliberate and return with the verdicts. So, Marko, you have about 45-50 minutes.
Thank you. Dear members of the jury, dear guests, both at the amphitheater and online, I'm going to present now my thesis titled Magnifying the Galaxy-Halo Connection in the Euclid Deep Field. It has been an internal endeavor of humanity to discover our place in the universe, to chart our way in it, to find how it all began, and what is its ultimate fate. To inquire these questions, we have devised robust scientific methods and we have built powerful instruments to look at the universe. And the most powerful of our instruments have revealed a 3D map of our universe, which in this slide I'm showing the map built by the Sloan Digital Sky Survey and its extended baryonic oscillation spectroscopic survey. The edge of this sphere marks the edge of our observable universe, the CMB, the so-called cosmic microwave background radiation, which is the first light that we can actually observe in our universe. At the very center, it is us, our galaxy, and this line marks the look-back time. Essentially, the further we look in space, the further back in time we see. And every dot, every colored dot here marks a galaxy, as observed by the Sloan Digital Sky Survey, in about more than 1/3 of the sky, billions of galaxies that map the distribution of them in our universe. Observation of the distribution of galaxies and of the cosmic microwave background radiation have revealed the energy density content of our universe, what our universe is made of, essentially. We now know that only about 5% is made of ordinary baryonic matter that we can actually see. The rest, about 70%, is dark energy, which is responsible for the accelerated expansion of our universe, and about 20% is dark matter, matter of mysterious origin, that is responsible for the way galaxies are distributed in space. And it's also essential to explain how galaxies, the rotational curves of galaxies. The map that I'm showing here has been built by the Sloan Digital Sky Survey. But very soon we'll have another very powerful instrument in space called Euclid. Euclid is a space mission of the European Space Agency that is designed to to investigate the nature of dark energy and gravity. It will observe about 17,000 degrees of the squared of the sky in its Euclid-wide survey, and will measure the light spectra and also shapes of billions of galaxies, which will be normal galaxies and densely sampled, which sets it apart from other surveys, for example. Euclid will measure the distribution of galaxies, they will measure how galaxies cluster together, and it will also measure how matter distorts the light incoming from distant objects in the universe. Apart from the wide survey, it will observe 3 deep fields of about 50 degrees squared, which will observe galaxies down to very early times in our universe. and will allow us to study how they have evolved through cosmic time. Studying the evolution of galaxies within the context of the dark matter is one of the central topics in my thesis, and especially in these Euclid deep fields. These observations of the distribution of galaxies have revealed the large-scale structure of our universe. Due to the action of gravity, matter has collapsed along the 3 spatial dimensions to create this web-like structure that we can see here. And we call it the cosmic web. It's made out of filaments which connect these filaments which encircle large nearly empty voids that connect to highly dense nodes. As such, dark matter makes the scaffolding of our universe. This is the skeleton. Here I'm showing the dark matter distribution in the Horizon Agent simulation. Galaxies closely trace the underlying matter distribution, but more so they are biased tracers. For example, more massive and luminous galaxies are more predominantly oriented in the denser regions. And galaxies here are circled.
Sorry, Marko, your screen is not shared to the people on Zoom. Yeah, can you share your screen with the slides? Yeah.
That's good.
Okay,
Sorry about it. As I said, galaxies are biased tracer of the large-scale structure. To describe this large-scale structure, a very powerful formalism exists that is based on a fairly simple assumption that all matter is partitioned in so-called dark matter halos. This is called the halo model and allows us to describe statistically the large-scale distribution in the universe. Within these hierarchical structure formation scenarios, small halos formed first, and they have grown through accretion and merging to finally create the cosmic web structure that we can observe today in the distribution of galaxies. Statistically, the large-scale structure can be described by one-point statistic, a halo mass function, which describes how many galaxies of a given mass in a unit comoving volume there are, as shown in this figure on the left, at different epochs of the universe. You can see that there are more low-mass halos, and that their volume density decreases with increasing halo mass. Furthermore, they can be described by a 2-point statistics, the 2-point correlation function, which measures how galaxies are clustered together, how much structure essentially there is at a given physical scale. And this figure on the right shows us that they're more tightly clustered together at small scales, and the amplitude decreases as the physical separation between galaxies decreases. Furthermore, more luminous galaxies are more tightly clustered together, another observational evidence of this biasing effect. How do dark matter halos in galaxies form? The initial lower densities of dark matter, due to the action of gravity, have decoupled from the cosmic expansion and have started to collapse under gravity. Initially, the dark matter was well mixed with the ordinary gas of baryons, which made only 16% given by this FB, the universal baryonic fraction. Gas, being subjected to all the known laws of physics, continued to cool down, to collapse, fragment. Furthermore, dark matter also can fragment and make such subhalos within this large halo, and this collapsing fragmented gas can ultimately form galaxies. Usually there's one galaxy at the center, which is called the central galaxy, and several satellites that can reside in their own subhalos within this parent massive halo. Galaxies can grow in these halos by forming new stars, which can be fed by cold accretion from cold streams that penetrate along the filaments of the cosmic web deep inside these halos. Furthermore, they can grow by merging with other galaxies incoming on the parent halo, and their star formation can be suppressed, galaxies can be quenched, meaning their star formation has ceased. This can be done by the hot gas in the massive halos, but also due to other physical processes. And for example, this hot halo can be kept hot by active galactic nuclei in the centers of the galaxies, which are powered by supermassive black holes, which can inject powerful jets of energy and keep the gas hot. From all of the above, it becomes clear that there exists an inextricable connection between the properties of galaxies and halos. And this is referred to the galaxy-halo connection. And studying aspects of it, especially the relation between their stellar mass and the halo mass of the galaxy of the halo, is the central subject of my thesis. To understand better this stellar to halo mass relation, I'll start with the dark matter halos, which, as I mentioned, can be described by this halo mass function. If we zoom in on a halo, it is populated by galaxies, and the way they are populated can be described by this halo occupation distribution formalism, which essentially describes statistically how galaxies populate halos of a given mass in terms of mean occupation numbers. And as such, it's a powerful tool to predict observables such as the correlation functions. The stellar mass of a galaxy inside a halo is connected to the halo mass by multiplied by the baryonic fraction, which is basically the available gas that can form into stars, times an efficiency factor of how efficiently can this gas inside the halo form galaxies. And similarly, galaxies can be described by the galaxy stellar mass function. And the important thing to see here is that there is a mismatch between the two. If all of the available gas transformed into stars, both would be matched, but there will be some offset between the two, given by the baryonic fraction. The fact that there is a mismatch between the two means that there are powerful physical processes that are acting more on small and on large masses that suppress star formation and prevent galaxy growth. The stellar to halo mass relation refers simply to the ratio between stellar and halo mass, and its function of a halo mass is given in this figure here, where it describes the regime where central galaxies dominate the stellar mass budget of a halo, and there is the higher mass regime in which satellites start to dominate. There is some peak at which this ratio is highest, which is about 10 power 12 solar masses, and as such, it can teach us how efficient the galaxy formation process was throughout the life of the halo. In order to study the stellar to halo mass relation, one of the biggest issues here is how do we measure the halo mass? Whereas it's relatively easy it's possible to measure the stellar mass of a galaxy because we observe the light emitted by the galaxy. Halos do not emit light. So there exist several methods to measure halo masses. Direct probes, which can be satellite kinematics and X-ray observations of clusters, and gravitational lensing observations of how the light from distant galaxies is deflected by the foreground dark matter halos. These methods can include galaxy-galaxy lensing and the magnification bias, which I'm going to talk about more later. Then there are empirical phenomenological models which use statistical observables of how from galaxy surveys to relate galaxy properties to halo properties from theory simulations. These observables are usually statistical, such as the stellar mass function, the two-point correlation function, and these are typically indirect probes. Such are the abundance matching, which essentially matches the halo mass function and the stellar mass function that I just described, and the halo occupation distribution modeling. Then on the other end of the spectrum, there are physical models which start from first principles. They use all the known models of physics in formal galaxy evolution, and such are hydrodynamical simulations, such as Horizon AGN, Illustrious TNG, Eagle, Simba, just to name a few. They're most predictive because they give us direct insight into which physical mechanisms act inside halos and shape the stellar mass and other properties of galaxies. However, they are limited by computational power. You cannot run many heliodynamical simulations and test all your known physics and how it acts on galaxies in halos. Measurements from the methods that I mentioned above have converged towards a measurement of the SHMR in the local universe, and a compilation of them I'm showing in this plot here. Shows the SHMR, so the halo mass ratio, it's a function of halo mass. And as I said, there is a peak, which peaks at about 20%, meaning that the galaxy formation process has been very inefficient in this. Only 20-30% of the barriers are converted into stars. At low masses, there are physical processes such as supernovae, stellar winds, and at lowest masses reionization that act in galaxies and suppress their star formation. At higher masses, there are AGNs that can keep the gas hot and prevent further star formation. These are called feedback processes. Despite these agreements at the low redshift, there are still a number of open questions about the stellar halo mass relation. How does it evolve through cosmic history? It is important to know that because it teaches us about the quenching efficiency of different epochs in the universe. And the literature is relatively inconclusive on this question. Different works give different results on its evolution with cosmic time. And this has mainly been due to the challenge to assemble homogeneous data sets with the same selection function at all redshifts and the same way to measure physical properties of galaxies and to measure the evolution through cosmic time in this homogeneous data set. Furthermore, the contribution from central galaxies and satellite galaxies in the mass budget of the halo throughout cosmic history remains poorly constrained. And this is important because it teaches us how quenching has happened for central and satellite galaxies. And answering these questions, understanding the cosmic evolution of the stellar to halo mass relation is the central subject of my thesis. Now, having laid down the questions that we're interested, what is the data that we need in order to inquire them? I'm going to start with the Cosmos survey from the Cosmic Evolution Survey, which is designed to measure, to study galaxy formation and evolution throughout cosmic history and its relation to the environment. And it is one of the best observed 2 square degrees of the sky, covered by all of the major facilities on Earth and in space. Here I'm showing the footprint of Cosmos as observed by several observatories, and this is how it compares to the size of the Moon. It's just a bit bigger than the size of the Moon. And it has a unique combination of depth, area, number of photometric bands, and spectroscopy. And importantly, it's part of the Euclid deep and auxiliary fields. From the latest observations in Cosmos, the Cosmos 2020 photometric catalog has been recently compiled, which uses the deepest to date wide observations in over 30 photometric bands, which I'm showing here. The depth of all these bands is a function of wavelength. And the Cosmos 2020 catalog is a near-infrared selected catalog of over 1 million galaxies down to redshift 10. And this is made possible by exactly using the near-infrared band as a selection to detect all the galaxies. And this is important because if you want to observe galaxies down to very high redshift, above redshift of 3, the spectral energy distribution of a galaxy that I'm showing here, these near-infrared bands sample the rest frame optical, which is essential to detect them and to measure galaxy properties. Furthermore, the depth in these bands, near-infrared, combined with the depth of the mid-infrared bands from the Spitzer telescope, its IRAC instrument, even longer wavelengths, allow us to sample the rest frame optical part of the spectrum, which is dominated by more evolved stellar populations in galaxies, and measure accurately the stellar masses of galaxies. And during my thesis, I worked on extraction photometry in splitter IRAC in channel 1 and channel 2, which are about 3.5 and 4.5 microns, which allowed to achieve highly complete samples of galaxies with accurate photometric redshifts and stellar masses to study consistently galaxy evolution from redshift 0 up to redshift 10. In this figure here, I'm showing the histogram of the stellar mass function of photometric redshift, and the lines show us the completeness limit of the catalog. Compared to 2015, the deeper near-infrared and mid-infrared bands allow us to go about 0.4 dex lower in stellar mass to assemble such highly complete samples of galaxies. Another survey relevant to this thesis, to my thesis, is related to the Euclid Deep Survey. The Euclid will observe in 4 photometric bands, 1 broad band in the visible, marked by IE, and 3 in the near infrared, Y, J, and H. However, if we want to observe, to sample more of the spectral energy distribution of a galaxy, we need to include more photometric bands. And including these photometric bands in the optical, in U, G, R, I, and Z, as well as from the Hyper Supreme Cam on board Subaru telescope, as well as IRAC bands which sample longer wavelengths, is what makes the Cosmic Dawn survey. It will combine Euclid, HSC, and Spitzer observations and provide an excellent data set of more than 20 square degrees of the sky, which will allow us to carry out, to study the galaxy halo connection from the local universe down to very high redshifts, with a lot of statistics given the large area. Having laid down the data that I used during this thesis, I'm now going to present the results. And I'm going to start with the stellar to halo acceleration in the Cosmos 2020 catalog. As I mentioned, the goal is to measure the cosmic evolution of the SHMR down to redshift 5 in this case. And I'm using the Cosmos 2020 catalog, which is a homogeneous data set of highly stellar mass complete samples down to very high redshifts. And to carry these measurements of the SHMR, measuring the galaxy stellar mass function and clustering by the two-point correlation function in 10 redshift bins, which are marked by these vertical lines. And furthermore, in each of these redshift bins, I'm measuring the two-point correlation function for stellar mass threshold selected samples, which are marked by these horizontal lines in each redshift bin. These measurements, I'm fitting them with a model based on the halo occupation distribution formalism, which has as a starting point a parameterized model of the stellar halo acceleration. Therefore, it fits directly give us a result of the stellar halo acceleration in all of these 10 redshift bins. My measurements of the galaxy stellar mass function showed how it evolves from redshift 0.2 to 5.5. Each of the different color-coded points and dashed lines corresponds to a different redshift bin, going from low redshift to high redshift. The low mass end of the stellar mass function is described by a power law, which has a knee at a characteristic mass m star of about 10 power 11 solar masses, and then an exponential decrease. Going from low redshift to high redshift, the slope first remains constant, but then it steepens, and the knee flattens out. I'm also showing a comparison, the halo mass function at redshift 0.35, which corresponds to the very first redshift bin, because we want to see how the two match. We see that at the low redshift there is this severe mismatch, which is more pronounced at low masses and at high masses. And as we go further in redshift, the shape starts to match better. And this teaches us that the feedback processes that act in low mass and high mass halo that were very powerful to suppress galaxy growth at low redshifts in the local universe become less and less efficient as we go further back in time. Next, my measurements of the galaxy clustering as measured by the two-point angular correlation function are shown for one redshift bin, 1.1 to 1.5 in this figure here. And it shows different color-coded points show us the correlation for different stellar mass selected galaxies going from low mass to high masses. And low mass galaxies have lower amplitude correlation, and high mass galaxies have a higher amplitude, which is another observational evidence of this bias in the galaxies with respect to the underlying matter. I'm fitting these measurements with a model based on the halo occupation distribution model formalism, and I'm doing the fits jointly with the galaxy stellar mass function, and these are shown by the lines, by the solid lines. At small scales, smaller separations on the sky, which corresponds to about 0.1 megahertz on a physical scale, the correlations here are described by the so-called one halo term, which describes how galaxies cluster together inside one halo. Then going at larger scales, they capture this so-called two halo regime, which describes how halo cluster inside within the large scale structure. And my fits agree very well with the measurements, although some discrepancies at the intermediate scales and at larger scales, which are dominated by the so-called integral constraint, which essentially the limited size of the survey, 2 square degrees, prevents us from measuring accurately the full power of large scales. These fits, as I mentioned, directly give us the stellar halo mass relation, which is parameterized by these models. In this figure here, I'm showing the results in the first redshift bin of 0.2 to 0.5. The purple envelope shows us the total stellar mass budget as a function of halo mass, whereas the dashed one shows us the central contribution, and the dotted one shows us the satellite contribution. The low mass regime is dominated by the centrals, and as we move towards higher masses, higher than about 2 times 10 power 13th solar masses of the halo, and it's the satellites that start to dominate the stellar mass budget of the halo. This peak efficiency is reached at about 20%, again indicating this inefficient process of converting baryons into stars and galaxies throughout the lifetime of the halo. Furthermore, what is interesting to see at high halo masses, which corresponds to group and cluster scale halos, the efficiency or the total stellar mass budget is still lower than the one at the peak, meaning even if we consider all the galaxies, satellites in the halo, the stellar mass budget is still lower than what is achieved at the peak, meaning that there are powerful physical processes that act in massive halos and that act on satellite galaxies and suppress their growth. An example of those are this hot halo mode, the fact that the halo is hot and the satellites live in this halo, which hot halo can be kept hot by this AGN feedback, but also there are physical processes that act specifically on the satellite galaxies, such as stripping, strangulation, starvation, etc. Furthermore, however, the model that I employed here is a phenomenological model, and as such, it relates statistically the properties of galaxies and halos, and is unable to teach us more about the exact physical mechanisms that are responsible for the quenching of satellite galaxies. And one way to peer deeper into that is to compare our results with hydrodynamical simulations, in which we know that we have a better understanding of what physical mechanisms are acting in these simulations. For this reason, on this figure, I'm showing my results in black compared to 3 state-of-the-art hydrodynamical simulations: Eagle in orange, horizon AGN in blue, and we will use TNG 100 in red. Starting with horizon AGN, we see that there is a huge discrepancy at low masses, such that horizon AGN there is much more stellar mass inside a halo, a low mass, than in our observations in the other simulations. And this can have been explained by the recipe of the feedback mechanisms that act in low mass halos, such as supernova feedback, that are implemented in this horizon AGN. And that is also observed in other observables, for example, the stellar mass function in these simulations is known to overpredict these low mass galaxies precisely because the stellar feedback implementation is less efficient than in the other simulations. Eagle and TNG agree much better on the low mass end, but then they are calibrated to actually to reproduce these observables at low mass and better. However, with all the simulations, the discrepancies are much higher at the high masses. Most notably, we see that the peak is much less pronounced in all the simulations, meaning that this high mass end is dominated by satellite galaxies. There is much more stellar mass, meaning satellites have accumulated more stellar mass in these simulations, which suggests that in the simulations, the satellite quenching is either inefficient or it happens late in cosmic time, allowing these satellites to grow higher in mass and accumulate much more stellar mass than what my observations tell us there is. In order to capture the redshift evolution of the stellar halo mass simulation, I'm showing here the evolution of the peak halo mass, essentially the peak of the SHMR. And my results are shown in the purple line, and I'm also comparing with population results from the literature. My results show us that the peak halo mass continuously increases with redshift, meaning that more massive halos were most efficient during their times because the peak captures is the peak of efficiency. At low redshift, there is relatively good agreement with the literature. However, at the high mass end, the low redshift regime is continuing, but the high redshift regime, the discrepancies between different observations are high. And we still don't have a consensus on what happens in high redshift. In our case, we are limited by the area of our survey and the number of galaxies that we have to observe at high redshift, which give us these large surfaces, these large error bars. Now, in order to peer a bit deeper into exact physical mechanisms, in this case, the case of cold flows that are responsible for the growth of galaxies, and putting my results in this perspective in the case of the cold flows. Now, the cold flows in hot media paradigm is essential to explain a range of observed galaxy properties, and they have been first established in hydrodynamical simulations by Clarence et al. And my goal is to see if this transition from hot accretion to cold flows happens at the peak halo mass. In this figure here, I'm showing the three different regimes. It's basically the halo mass function of stellar mass in which cold accretion can happen below this about 8 times 10 power 11 of halo mass, below which cold accretion can happen. In this regime, in more massive halos, the gas is shock heated and it's called hot accretion. However, there is this line that delineates the regime of halo masses in which cold flows can happen in hot media. These lines have been, there's an analytical prescription of this in Dekel and Grunwald, which is based on simplified assumptions and toy models. And in order to investigate that, I'm putting my results into perspective of recent measurements of this boundary between hot accretion and cold flows, namely by the recent results from Dalia et al. 2022, a paper which uses the bending of the star formation main sequence to convert the stellar mass in which this bending of the star formation main sequence happens using the SHMR calibrations from the Ruse et al. 2013, and these results are shown in the red circles, and they correspond relatively well with this boundary of hot accretion to cold flows. To check if this is true, using my calibrations of the SHMR, I'm using the same M star, the bending stellar mass, and I'm using my stellar to halo mass relation to compute the halo mass at which this transition might occur. And my result, the results using my stellar to halo mass relation are shown in the purple stars, and they agree remarkably well, especially at the low redshift. In the high redshift, both stellar SHMR calibrations show us that the bending of the star formation main sequence tells us that this cold flow, hot accretion to cold flow might happen at the flatter slope, which is indicated by this. And finally, I'm plotting in purple and the open line my observations of the peak halo mass, and it shows us that the peak halo mass increases, and at low redshift it falls a bit above this shock limit, but then the slope of the high redshift is still flatter. And essentially my measurements add another argument that this transition from hot to cold flows happen at flatter slope, which is also indicated by recent studies, including simulations, compared to what has historically been estimated by the model. Okay, so the results that I just presented are all obtained using this phenomenological model that indirectly probes dark matter halos. Now I'm going to present my investigations of an additional probe that directly probes dark matter halos, which is based on gravitational lensing. And this is the magnification, or precisely the magnification bias. To explain the magnification bias, we can look at this figure here, the left of which shows us a uniformly distributed galaxies in space in the background, which we can call the sources. And if we put a lens in the foreground, the total matter of the lens, including luminous and dark, will induce a change in the number density of the background sources. And as such, this change of number densities of background sources can be measured by, induces eventually a positional correlation between two samples which are separated in redshift. And that can be measured by the two-point cross-correlation function. And it linearly scales with the slope of the number counts of the source sample, meaning the steeper the slope, the more bright the source galaxies are in the background, this higher the amplitude. And it's also directly related to the projected over density that can be measured by the convergence. It is important to accurately separate galaxies in two samples of lenses and sources in redshift, because if there's any overlap between the two, or if there's interloopers because of outliers in the photometric redshift, for example, use photometric redshift to separate the two samples, and there's such an overlap, then that will introduce systematics from clustering, which will add another term. And if we measure the cross correlation with overlap with interloopers, we will erroneously measure clustering signal interlooping with our magnification, which is a source of a severe systematic error in magnification measurements. Magnification offers several advantages. The most important one is that it does not require shape measurements, as it is the case, for example, galaxy-galaxy lensing. All we need is to measure the positions of galaxies and its flux, as well as its redshift. This allows us to go further in redshift than shear-based probes, because shear-based probes need to measure the shear, which is difficult to do at increasing redshifts. And the ingredients that we need to measure magnification successfully is deep surveys, which are complete down to faint magnitudes, which can be about 26 maybe, and needs accurate photometric redshifts to cleanly separate foreground and background samples. Because as I mentioned earlier, if we don't do that, we have severe systematic errors. And as such, it offers several opportunities. It can allow us to measure halo masses for population of lens galaxies in tomographic redshift bins, and measure halo mass profiles in clusters, for example, allow us to calibrate mass coincidence relations, and as I just mentioned, measure the properties of also accumulation of galaxies in different tomographic bins. And the goal of my work is to investigate how well magnification can be measured in the Euclid Deep Survey to probe halo masses at high redshifts beyond redshift 2, and also simulate photometric redshifts to investigate the selection of background and foreground samples. I'll start by showing the results of the Cosmos survey as a pilot study for Euclid Deep, because Cosmos is part of Euclid auxiliary fields. And I'm measuring magnification with a 2-point angular cross-correlation function for photometric redshift and stellar mass selected samples of galaxies, which are shown in this plot here, lenses and sources. This figure here I'm showing the correlation due to magnification of lenses at 0.5 to 0.8 in redshift, and different color-coded points correspond to different stellar mass selected samples, showing us that low mass galaxies have lower magnification signal and high mass galaxies which have more higher magnification, which is what we expect. Lensing is stronger around more massive galaxies, more matter, essentially. I'm fitting these measurements with a model based in the halo occupation distribution jointly with galaxy stellar mass function and clustering, the previous measurements that I showed. And these fits are shown in these solid lines. So first of all, as we can see by the error bars, magnification is not really measured with a high signal to noise ratio. This is because of several things. First, lensing in general is not a very strong effect, and the amplitude of lensing is low. And furthermore, magnification is even weaker effect, and Cosmos being a limited survey in terms of area for lensing standards contribute to this relatively low signal to noise ratio, which makes the constraining power of this model, joint model of the stellar mass function clustering with magnification being completely dominated by clustering and galaxy abundance, meaning that in this case, magnification cannot really improve the constraints of the SHMR parameters, as I mentioned, because of the limited area and sample size of Cosmos. However, magnification offers other degrees of freedom, which is promising to constrain other halo properties. For example, we see that there is a difference between the models and the measurements at small scales. And one explanation for this can be the basic assumption that most often is assumed in HOD models that they follow, the satellite distribution inside of halos follows this NFW profile, the same NFW profile as the dark matter density inside of halos. But is this really true? And magnification, being a lensing probe and sensitive to the inner profiles of halos, can actually open us these degrees of freedom and investigate these assumptions that are usually made in the HOD. Finally, to investigate the prospects of magnification inside in Euclid Deep, I'm using the flagship 2 simulation, which is an official Euclid dark matter simulation, which is one of the largest simulations made for Euclid. And more specifically, I'm using its mock galaxy catalog to measure magnification by emulating the Euclid Deep survey. The point here is to measure, to investigate how well magnification can be measured in the Euclid Deep plus HSC survey strategy, which will be the cosmic dome survey, about 20 degrees squared in the sky. And I'm measuring the 2-point correlation function for this magnitude and stellar mass selected samples. In this figure here, I'm showing the cross correlation between lenses in the stress tube bin and sources of 2.5 to 3. Different curves show us the measurements for different visiband magnitude selected samples, because, as I mentioned earlier, magnification scales linearly with the slope. More massive galaxies or brighter galaxies have a steeper slope, therefore higher amplitude of the correlation, and this decreases with decreasing magnitude. And we observe this correct scaling with the source magnitude cut. Now, to investigate if these measurements agree, the magnification actually measures the observed, the true projected over density. I'm computing that in the simulation, computing the convergence profile, which we know because it's a multi-galaxy catalog. And that is shown by the black curve here, scaled by the slope of this sample here. And as we can see, it agrees very well in shape, although a bit of a difference in amplitude. But this agreement in shape tells us that indeed magnification, as measured by the correlation function, can measure the projected over densities and halos, and therefore measure halo properties. Finally, as I mentioned earlier, photometric redshifts can introduce clustering systematic errors in magnification measurements. And my goal in this work is to investigate will photometric redshifts in the Euclid Deep and cosmic dawn survey strategy be good enough for magnification. And for this purpose, I'm simulating photometric errors and photosets, and I'm measuring photosets with easy, because these are actually not provided in the version of the catalog that I had available at that time. And I'm measuring photoset selected samples, magnification for them in for lenses at 0.5 to 0.8 and sources at 0.5 and 3. And these measurements are shown in this figure here. The photoset selected sample is shown in blue, whereas the true redshift selected sample is shown in red. Yeah, just as a side note, all the measurements that I showed earlier were selected in true redshift for the Euclid mock catalog. But here, the fact that the true redshift selected and the photoset selected sample magnification measurements agree, and the fact that when I turn off magnification and measure the cross correlation of photoset selected samples but with no magnification, and if there was any outliers and interloopers in the photoset, then this amplitude will not scale, will not be consistently zero. In our case, it is relatively consistently zero, which confirms that the photosets of Euclid can allow us to measure, will allow us to measure magnification in a Euclid deep survey strategy. However, the selection needs to be done carefully in order to minimize the photoset outliers. Just to summarize this investigation of magnification in Euclid deep, as I mentioned, will allow us robust magnification measurements to probe halo properties for different lens galaxy population, because we have a large area and a lot of galaxies, statistically, numbers of galaxies to probe for different galaxy properties. And the next step of this work is to infer actually the properties halos from HOD modeling, the magnification correlation, and investigate other sources of systematic errors. Finally, I will just highlight some other works that have been part during this thesis, especially in the last several months of my thesis, and both relate to observing one of the most distant protoclusters known to date and the most distant galaxy, potentially the most distant galaxy known to date, using the data in Iraq that I processed during my thesis, combined with Herschel. We searched for overdensities, which later observed with Noema, and found detections of CO423 lines, and have found potentially a galaxy cluster at around redshift 4.2, which places it among the 3 highest redshift protoclusters known so far. And then using the latest JWST data from NIRCam in the SMAX cluster, using PhotoZ and dropout selection, we have identified potentially the highest highest redshift galaxy known to date, which of course is not confirmed and is subject to follow-up proposals and observations in spectroscopy to potentially confirm its nature. I'll just finish with some future prospects. So the results that I highlighted in my thesis, still continue the debate on what happens in massive halos at high redshift, and this debate remains open. And there are two surveys in particular that will allow us to probe this high mass at high redshift. And one is the Cosmic Dawn survey that I talked about earlier. Its large and deep observations will allow us to constrain high masses at high redshift. And then the Cosmos Web survey, deep JWST observations of around 0.6 square degrees will allow us to probe the SHMR down to deep observer ionization around 6 and higher, but also its exquisite resolution will allow us to include lensing measurements to high redshift based on the shear probe. That was all about my results, scientific results. I will just conclude now. So during my thesis, I did a complete analysis going literally from pixels in images of multi-wavelength photometric surveys, part of the Euclid, to modeling, to measuring observables of clusterings in stellar mass, modeling the HUD, doing fitting, and inferring the cosmic evolution of the stellar to halo mass relation. And as such, they provided first measurements of the cosmic evolution of clustering, the central and satellite stellar mass function, the evolution of peak halo mass in a homogeneous data set, importantly, the Cosmos 2020 as well. And my measurements of the scientific results question our satellite quenching models, especially as implemented in hydrodynamical simulation, which is the discrepancy that I talked about earlier, and confirm a flatter hot to cold accretion transition. Finally, investigating magnification. As a direct probe of halo properties, I showed that it can be accurately measured by the Euclid Deep survey, provided the selection is done carefully. And here I'm finishing my presentation. I thank you all for your attention.
So we now enter the question and answer session. I will ask